So in this lesson we will look at what is design for manufacturability vis-a-vis the way things are done at present in the industry, how castings are designed and manufactured at this point of time, and how things are changing where designers and manufacturers are collaborating. So we will look at that, and we will also kind of from this lead on to some of the guidelines for DFM and how do we evaluate, because some guideline may say do this, some guideline may say do that. How do we put a number to that? In a sense we have been learning about how to put numbers in this course, from shape complexity to various other feasibility and fillability and all that, but we will try and do that for DFM also as part of this or overall strategy of quantitative evaluation instead of qualitative evaluation. That is the whole theme. So let me start off with this cartoon. I think all of you will enjoy that. People say we will do teamwork and we do things in parallel and so on, but things in parallel are okay as long as you plan it very well. Because remember, serial thinking is very easy because you are starting the next activity only after the previous one is over. The moment you want to do parallel, it imposes an additional constraint of much better planning, much better coordination, cooperation, communication and so on. So let us go back to how things really happen in industry. Today we have common canteens because management says everyone should eat together, from top management to the worker level to design and manufacturing and tooling and planning and costing and finance, everyone they sit eat together. But I always go and notice and when I go to industries where they eat commonly, I ask them, okay, so that table who are the people? They say, oh, they are all finance people. I said that table who are sitting there, oh, they are all supply purchase managers. So although you have common canteen, the idea is to mix. So people are comfortable with their own breed, so they will continue to keep the walls okay between them even after that, even after common canteens. So what really happens is these cultural walls between various departments, and here we focus on design manufacturing department, really promotes, which is not a good thing, one-way communication. So what happens initially, the design department will create the drawings, they don't even consult the manufacturing, then they throw the drawings over the wall essentially in a sense to manufacturing. And usually designers think the design is holy, and they don't, we know best how to design, so why should we ask anyone else? We have all these CAD CAM tools, FEA tools, so why should we ask anyone else? The manufacturing people also have their own ego and prestige issues. Oh, we can manufacture anything you design, no problem at all. You want to put undercuts, no problem, multiple cores, no problem, complicated holes, no problem, we will manufacture no matter what the cost, no matter what the rejections are, but we will at least make one piece good out of 100 pieces, right? Prestige issue. Okay. Also what happens is the way projects are done, and I am talking about a life cycle of a project, let us say building a new car and then you have a new engine in that. Initially, and let us say the total project time is 8 months or 1 year, the design will take its own time because initially there is no pressure, they will take maybe 4 months to design the car. Then they will say no, this whole project has to be over in 8 months time, you have only 1 month to do the tooling or 2 weeks to do the trials. So pressure shifts to manufacturing little later. So the pressure is not balanced, and usually pressure comes as a surprise. If only manufacturing knows that okay, I am going to get this perhaps sample production next month, he will start preparing for it mentally. Maybe he will start ordering for the right kind of material or inform the tooling guy, hey, I may have an urgent order for you next month, be ready, keep some time free. That advanced communication really helps. But no, they get it a surprise, right? So this one-way communication over the wall and this ego clashes and the walls between them don't really help. What really helps, what really results in, because of that, again one more cartoon to show you, that what was proposed by the marketing group or the corporate group, and what is designed and what is manufactured and what is finally supplied, and what a user says, no, but I thought I said something else. And if you remember, I told you in the first day that most of the problems in manufacturing and life as well are because of mismatch of expectations, right? Now what are the reasons for that? Now we can always justify why it happens, right? We can say it happens because, oh, casting is a very complex process, too many design parameters, too many material parameters, process parameters, and these parameters have a complex interactions between them. We don't really know the combination of this thickness with that material with this temperature, what happens, no one really knows, there are no data books. So we can always take shelter around that excuse, okay. Another excuse and another reason is that, okay, the designers, manufacturing, tooling people never talk to each other properly. They only fight with each other, they don't communicate with each other. And one more reason they cite is that, okay, foundries, we're sorry, we are not getting good people, and our senior people are leaving all the time, we are not able to pay them well. If we pay them well, we have to increase your costs. How do we manage that? Life is very difficult, right? So these are all the reasons, or you can say excuses, either way you want to look at it, for the reasons why the as cast part and the as design part is a huge mismatch, and we are discussing yesterday also. As much as 10-15% weight difference, sometimes even after machining, okay, at least 5-10% difference. So let's introduce a concept here. Okay. Design for manufacture is what is currently done. All we are looking at is something has already been designed, and all we are talking about is how do we manufacture it as efficiently as possible. The scope is limited once the design is already frozen. All I can talk about is how do I maximize or minimize my material consumption, minimize my yield, my energy consumption, maximize my yield, and so on. But if I talk about a new way of doing things, design for manufacturability, design for manufacturability, and this is what the true DFM is all about, not the first DFM, both are DFMs, okay, where we are talking about good compatibility between design requirements and process capabilities. Or another way, we also talked about how do you make robust designs, designs which are more compatible with the process and less sensitive to variations in process parameters. Okay, who should do this? This DFM should be done by DFM team in design team in collaboration, cooperation, communication with the manufacturing team. Also, the difference between these two, in one word, if you say, the first DFM is reactive. Something has gone wrong, it is a post-mortem method. Okay. And the second method, the new DFM or the true DFM, is pre-mortem. You are predicting and preventing a potential problem, right? So this is much better way of doing that, and it is not a tool or a software. It's actually a culture and behavior. So DFM is far more than just using some rules or tools or something like that. So we need to really go deep into this. Now, we also always need some business, we say business reason for doing this, and there is a straightforward reason for that. If you look at number of design changes, okay, in the part design stage, or tooling development stage, or manufacturing stage, usually they do come down. Designers do evaluate several options before they freeze on to the manufacturing drawings. Okay, but if you see if you see the type of changes in design, there may be major changes. They may completely put this feature there, or put a hole there, or remove that. Major changes happens in design. As you move towards tooling and manufacturing, that the quantum of change or the amount of change reduces. In manufacturing, you are just playing with just a little bit of wall thickness or a little bit of fillet. They are not major changes. Okay, so that is one way looking at it. And also, if you look at the goal of the task, the change. Okay, when you are in the initial testing of concept stage, the reason for manufacturing is just to make a prototype and see whether it works, functionality is okay or not. You are not worried about cost or quality at that point of time, in a concept stage. As you move to manufacturing or design for manufacturing stage, the conventional regular manufacturing stage, the idea is all about I want to do mass production. And mass production, all my idea is, okay, compared to prototyping stage, I want a low cost or lower cost. Okay, that's okay. And let us say that is my baseline cost and baseline quality. Baseline means some number which I can compare. But the moment I say DFM, I am now specifically targeting, can I produce the optimal quality at the highest quality at the lowest cost? How do I get the total lowest cost of a life cycle? Not just design or manufacturing only, but the total life cycle cost. And also, if you notice, if you make any change in the manufacturing stage, one point, the bottom right point here is, any major changes at the manufacturing stage are very expensive. So you don't want to do that. And we'll see this again in another cartoon when you look at the costing. So I'm just turning the thing upside down. If you remember our first day, we talked about a design is nothing but material and geometry and tolerances, okay, which drives the selection of the process or design of the process, which includes selection of the equipment, the design of the tooling, and finally the kind of process control you want to put forward. Okay. and that affects your quality and cost and productivity. What we also said is that as you keep doing these experiments on the shop floor, every new casting is an experiment. Okay, not only development, also regular production, every casting is a different casting. So if you can somehow capture this data and say that, okay, in this casting I had really pushed the limits of wall thickness, and okay, in 3.5 millimeters I got okay quality, but 3.25 I start getting problems when the wall thickness exceeded, wall length exceeded so much length, and my temperature fell below this thing, I start getting misrun or cold shed. Now that critical information you are generating all the time, but it is not going into any your own best practice manuals. Okay, if you start capturing that data and create what is called as technology database, not material property database which you are talking about all the time, but technology database. And there is a need for a massive national mission for generating these databases for metal casting for all possible combinations of metal, process and geometry. Okay, this is an important slide. It will get very complicated, so I am doing it step by step. This gives you in a nutshell overall integrated approach to designing of part and tooling and process, which should give us, if you follow it nicely, it should give us a casting which is right first time and right every time. Perfect casting is what we are talking about. Okay, so at the designer end, which is like say OEM, okay, a designer just creates a 3D model and then does of course FE analysis, but at the end of that, before he freezes the drawing, can he do a little bit of feature check? And we'll look at in the next lesson what I mean by feature check. They're essentially wall thickness and core hole diameter and some thickness gradient and things like that. If you can just do a little bit of feature check, and then feature check tells him, oh, I'm putting the two holes too close together. Okay, and can I now move it back? That's a feature check, and immediately I'm doing a little bit of optimization of DFM there itself. Once it is okay, then I send it to my tool maker, and the tool maker also doesn't do one-way traffic. He also does a little bit of local check saying, okay, so I did a bit of NC tool path planning or machining, and I am seeing a bit problem where I'm not able to get the right fillet or a right undercut. Can I do a little bit of tooling change? Okay, local change, a small change. Okay, and you optimize the tooling. Maybe you have to also optimize the parting line and course and your allowances and then things like that, layout and all that. Once he is okay with that, then you go into the methoding stage. That's when you look at your actual orientation and maybe risers and gatings and things like that. And there you can use your simulation to see that your gating and feeding is right. Okay, and you get the quality right by simulation. Once that is okay, then only you go into the foundry stage where you're doing the last bit of process parameters. Okay, what is my sand composition or coating I should use? Ideally they should be done at the previous stage. In fact, ideally everything should be done at the previous stage, but at least you are doing the final planning of your production scheduling and your production planning and things like that. Then you might get a perfect casting, might get, I said. But ideally what we should do is at every stage, if we can somehow feed the information back to the previous stage, from your process planning to methoding, from methoding to tooling, from tooling to designer. In fact, all these bottom stages to designer eventually, if you can do that, okay, then we are talking about not only a good collaboration between all the 4 stages, but also automatic, and if you do it using information technology tools, automatic capture of the knowledge which is involved in the whole process. Now, obviously everyone cannot do everything on day 1, but if we can keep moving on that, we are moving towards perfection. Okay. So every level you go back to previous level also, all the previous levels also. Previous level only you get immediate collaboration and fine tuning between those two, but if you go back little more, one further level up, they start appreciating your problems. Designer suddenly says, oh, you increase the copper, why did you increase the copper content in this? Then you say, okay, I wanted to do strengthen some area where you are not getting enough strength or something like that. So they start appreciating your problems. The question here is, how much information you want to share with designers? So sometimes sharing of quality information or cost information helps you to, instead of being adversarial position, you are collaborating instead of competing or in a way, pushing each other.
Sir, I can add something more also, because I have been doing the same thing with my foreign
Excellent.
buyers and all, because they always ask for the cost breakup of the entire component. The thing is that the comment comes suppose we have put this amount for the machining, they will say, "Arey Baba, you are charging too much for the machining. It should be something less,
Yes.
or your this process cost is very high."
Yes.
So at least
You get a feedback.
considering it in a positive sense,
Yes.
we start thinking on that direction that how to bring down that cost.
It depends on what kind of relationships you build with them. I also found that moment you start sharing information like this, instead of that, one-time affair kind of a thing, it becomes a more longer relationship with OEMs. They start trusting you. They know that you are there for, and so on and so forth. So
if we start involving these suppliers,
Mhm.
and if we consider them as partners,
Exactly.
and involve them in different stage.
Great. Now let me give a very simple example. Okay. This is a very humble theoretical example of a bracket. It's not a practical example, but you see some design issues or manufacturability issues here. Okay, you have a sharp corner, so you know it can get a turbulence, and then now you know all these things, right? And then you can get erosion and so forth, and so sand inclusion. Okay. In the middle you see a thick section, so now you know they will get a hot spot, you will get a shrinkage porosity. That's another quality issue. And somewhere here you see a thin rib. Let's say it's too thin. It might have a premature freezing, and then you might get a cold shut or a misrun. And if that's undercut, a little complicated undercut, which also comes next to the core, makes my core little more complex and core box little complex, so my tooling cost can go up, right? Now, can I solve all these problems? Or if a designer appreciates that, he can change the design like that. If you now you see there's a little rounded corner, so metal can flow more smoothly, and then you have and that rounding also takes care of the wall thickness reduction there, so you might get a lesser shrinkage porosity there, or easier to feed with a smaller feeder. That the two ribs at the two ends have been moved to one in the center. So now parting line, there's no undercut in the middle of that, so you have core becomes a little more easy. And so that's one nice theoretical example of how designers can make the part more foundry friendly. Okay, of course, life is never so simple. So you have made a big hole, a small hole now. So if a small hole in a thick section can lead to sand fusion, and so you can have a different problem. But then you can do our so-called optimization and say that, okay, between the four problems, this is a lesser problem, so I'll go ahead with this. Okay. Now let's go into how do we actually put a number to this, because if you see the previous slide, I have several changes, but how do I know that how much to reduce thickness or how much to add a fillet? How do I quantify that? How much is just right, how much is too much? Okay. For that, you can start putting it in a what I mentioned earlier as technological database. This is a simplified version of that. I'll make the picture more complicated in a minute. But if you see normally what foundries say, if you say my wall thickness, let's say a HPDC guy on a particular metal process range, he says, I will take any parts which fall in the range of 2 millimeters minimum wall thickness to 8 millimeters minimum wall thickness, I'll take those orders. Beyond 8 millimeters I will not touch, below 2 millimeters I will not touch. He says that as a normal basis. But life is not really like that. Do you mean to say that 1.99 millimeters he can't make and 2.01 millimeters is perfectly fine? It is not really like that. So life is what I call as a fuzzy. By fuzzy I mean that if supposing he gets an order of, let us say, 1 millimeter in a small section, not a very long section, okay, and the customer says, come on, the overall part thickness is 2 millimeter, 3 millimeter, but here just there's a little bit of 1 millimeter here, can't you do something and produce a part? And the foundry will say, okay, it's beyond my limits, but maybe I can put a heater there or something else, or put the gate somewhere close to that. Okay, I'll manage it. But remember, he is managing it. So once you go into the yellow area, you can make it, but with some penalty of quality or cost, right? In the green area, I'm absolutely comfortable. Red area is no. If it's giving below 1 millimeters in PDC, I'll say forget it. It's impossible. Go to investment casting people. Okay. Similarly on the other side also. So any capability can be put into three ranges. Like our traffic lights, red means no question. Yellow means okay, I can manage, but I have to be watchful. I have to be careful. Supposing I have a part which has 10 millimeters wall thickness. You know that up to 8 millimeter wall thickness, I get a clean quality. And I know that beyond 11 millimeters in this picture, the red starts there. I don't want to touch that. I cannot produce it with my machines or my process or my pressure, whatever it is. Supposing some part has 10 millimeters, which falls in the yellow zone. So is it yes or no? How much is that? Can I put a number to that? So if you map it, if you see the value at 10 millimeters wall thickness goes and touches the graph at a value, if you go on to left side, 33%. So I say now I say that the compatibility between my part design and process capability is 33%. If my part wall thickness is between 2 and 8, I will say my process capability is 100%. And if it's between beyond 2 millimeters, I say it is 0%. So I can put a value to that. End of the day, I keep saying that every foundry must find their own niche. If you can have a niche of GMP, geometry metal process combination, which no one else can do, I think you are in a good shape because you are a worldwide supplier now. You are a world leader in that. So let me now put this in a proper definition. So what exactly is design for manufacturability? So in a way I said the three elements of that are, what a designer does is that he selects the material. For a given material he selects the geometry, okay, and then he is doing that, he is specifying what tolerances I want the geometry to be within, okay, and finally what is his goal? He has to satisfy the functional requirements of the part. So to satisfy the function, he is specifying the geometrical design and the material specification and the process tolerances. By tolerance I don't mean just the dimensional tolerances, but also the property tolerances like strength tolerances, things like that, all kinds of tolerances. Now what does the manufacturer does? Typically he just does and decides the process, but now we are adding an additional step called let's do a manufacturability check also. What do you do in that? You check, okay, my process capability is this, and if you can start producing those charts for your own organization, your own foundry, you have a quick check. Okay, design minimum wall thickness, maximum wall thickness, core diameter, core aspect ratio, distance between core, just a tick mark. If you have 10 parameters to start with, great. Next year you have 100 parameters to check, no problem. So do a quick check of that. But then if you can get together with the designer to optimize the part geometry, keeping functionality same, but little bit of adjustments of material, okay, or even tolerances. You ask the designer, why do you want plus minus 0.5 millimeters there? Can I do it plus minus 1 millimeter because I am using manual molding or this kind of process, can I manage with that? And designer says, okay, 1 millimeter there should be okay, okay, go ahead. So question everything, his tolerances, dimensional, strength, properties, whatever it is, okay. So if you can optimize the part geometry, well and good. Otherwise you have to change the process, or in the worst case, maybe worst case for you also, you have to say sorry, you can't do it by sand casting or shell molding, you have to go to investment casting or LPDC. You may have to recommend a change of process. So in this lesson what we have just talked about is that conventionally the way companies design the part first and then do tooling and then do manufacturing, serial engineering, is not good because you find problems when they are too late to be fixed easily. What we say is in general at the manufacturing stage it is easy to see the problem but difficult to fix it. At the design stage it is easy to fix the problem but difficult to see what could be the problem, okay, right. Manufacturers don't have design rights and designers don't have manufacturing knowledge, am I right? All these one line statements, all these pack a lot of cultural let's say guidelines, okay. So what we are saying is if you do the true DFM, design for manufacturability and not manufacturing only, you are trying to predict and prevent potential problems early in life cycle when it is easy and less expensive to do that. And end goal is that you make the part requirements and process capabilities as matching with each other as possible in the green zone, as much in green zone as possible. If all parameters are in green zone, great. Even if one parameter is in red zone, you cannot go ahead with manufacturing with that process and you have to go back and change something. So in the next two lessons we will look at what are those parameters, how do you check them, and a few examples of how they were used to actually solve a problem, okay.